This section deals with iconic persistence or iconic memory, which is a term for a very brief storage system, purely in visual form, that holds a brief display, and by iconic memory or iconic persistence, we are not talking about the visual spatial scratch pad. And the difference is that, first of all, the visual spatial scratch pad can be rehearsed, and we saw the mechanism for rehearsal is actually the planning of movements, in particular eye movements, in space. The iconic memory or iconic persistence is a storage system that's much briefer than the visual spatial scratch pad, much briefer, and you cannot rehearse the information. It passively decays, so we think of it as a passive storage system. But the question is, what happens if I show you a brief display, let's say consisting of a set of letters like this, 12 letters, and your job is to report as many as possible. And by brief, I might show the display for 1/10 of a second, for example. And the claim is that all of the letters enter some kind of storage system, which we call iconic memory, and it holds a lot of information. The problem is that when you report the information, as you are reporting, which takes time, so the actual contents of iconic memory is decaying. And so if you choose to report, for example, the first row, by the time you've hit the letter J, which has taken you quite a lot of time from the beginning of the first letter to J, the rest of the icon will have decayed. So what we call full verbal report, will seem to indicate that just a few letters are available. But people will tell you, I'm convinced that I saw many more letters than I was able to report. I just didn't have enough time to report them. And of course, it means that the letters are lost from this brief display and that you were not able to transcode them into more durable form. So how can we test the idea that there's some form of buffer, iconic memory in this case, that temporarily holds much more information about the visual display that can be reported in a task like this one. And so imagine I show you now it's 12 letters, but it's 2 rows of 6 in this case. And we want to show that there are many more than just 4 or 5 letters that were registered in iconic memory. And in fact, the claim is that you may have actually apprehended all 12, but you quickly lose them so that you're left with 4 or 5. And how can you prove this? Well, the analogy that we can draw on is what happens when I give you a standard academic exam made up of, let's say, 40 questions that cover weeks and weeks and weeks of lecturing and study on your part. And the answer, of course, is that we sample at random. We can't ask you thousands of questions, but we ask 40, and the idea is that the 40 cover all the space of possibilities that you had to study. So the idea is similar here. I give you 12 letters, and I sample a subset of the letters at random, and if I can report any of the subsets, if it's even just one, but it could be 3 or 4 at row or a letter, depending upon the task. But if I can report any item or set of items that you ask me to report, then I surely have had access to all of them, assuming that reporting is random. So I cannot pre-select a particular letter. And if the reporting queue, that is a little line, let's say, above a letter or row, if that is presented after the display is turned off, so that's the critical part here, that means that whatever you're selecting from cannot be on the retina anymore because the display has been turned off. And so what I'm reporting then surely must be from memory, and that's the amount of information in iconic memory. And so the inference is that if I can test after the display is turned off any one of the letters at random, and you can report that letter, that means I must have had access to all of them at some brief interval. So if the representation of the display fades too quickly, to allow me to report all the letters, then this method of queuing a randomly chosen element in the display, again, after the display is removed from the screen, that will tell me the availability of all the items, and this is known as the partial report method, which means you are sampling at random from the display, and I'm reporting just a partial percentage or individual item of the display. Could be one item or a subset of 12 letters, let's say. If I can report all of them at random, I must have access to all of them at some point. The simplest version of the method is to show 12 letters in 2 rows, so 6 per row, and I give you a spatial cue indicating which letter is to be reported. So here's an example. You see this display. There are 12 letters. It is removed from the screen. You actually shown the letters very quickly. I'm showing them much longer here just to get you to look at them. But imagine you saw this for a very brief interval. The letters are removed, and now I give you a bar under the location where one of the letters was. It's no longer there, but the letter was there, and you are asked, what was that letter? I'm queuing any one of these locations at random, so you cannot selectively attend to anything until you see the bar, and the bar is queuing a blank region on the retina or in space, but there's something in memory that presumably I can use the bar to report, and I say it was a T. And this procedure yields a very robust result. You can report any letter queued at random by the bar marker, providing the queue occurs soon enough after the termination of the display, meaning the display is gone and there's a very short delay before that little bar occurs. The shortest delay would be 0, which means the minute the display disappears, the bar appears in a particular location. And because only 4 or 5 letters can be recovered in a full report task, meaning if I ask you to report as many of the letters as you can see without partial report, you're going to get just a very small subset. We can only get 4 or 5 letters when you do that, but nearly every letter is available for partial report, so we infer that many, if not all of the letters, must be briefly registered before they fade away. On the average, partial report yields an average of 80% correct, or a little bit more than that. So about 9 or 10 out of 12 letters. It's not perfect. It's not 12 out of 12, but it's high. It's many more than 4 or 5. It's 9 or 10. The fact that it's not perfect could be due to all kinds of irrelevant factors, meaning it's there's a moment before you can match the bar to a particular location, and during that time where you're doing some sort of spatial computation, you're losing some information from the icon, assuming the icon display fades very quickly. So the fact that you don't get 12 doesn't necessarily mean that all 12 are not present. It just means that whatever we're using to queue report involves itself a delay, some delay in accessing the icon. So how long does the icon last? And we can use the partial report procedure to determine the duration of iconic memory representations by varying the delay between the disappearance of the 12 letters and the onset of the report queue, because the longer you wait before queuing a particular location, the more time has passed for the information in the icon to decay. And in the limit, if you wait long enough, we can ask how much information will you be able to report, and of course it'll be the same as full report, because you're waiting and waiting and waiting for the queue. There's nothing left in the icon to queue after enough time because the content has decayed away, and I'm left with what I could perceive directly using full report methods or processes. So if I'm looking at the top row, for example, I will report 4. You didn't tell me which letter to report yet. By the time you actually tell me, I've lost everything. And I will, on the average, be able to report 4 accurately. So if you happen to probe the letters that I already downloaded, if you want to use that term, then those will be accurate, but it's going to be 4 out of 12. And so you can see that here in the result. So here is the letters available out of 12, and you can see I'm getting close to 10, or the subjects are getting close to 10, when there is zero delay between what? It's zero delay between the offset of the 12 letters, meaning the letters have gone, they're no longer present, and they were up on the screen for a tenth of a second, then they are gone, and then there's a bar over one of the letters, but the location of the letter rather than the letter itself, because the letter is gone. And if there's a zero delay, you get 9 and a bit. If you wait even 150 milliseconds between the offset, the disappearance of the 12 letters, and the onset of the bar over one of the letters, again at random, you're down to around 7, give or take. If you wait 0.3 of a second, or 300 milliseconds, you're down to 6 out of 12. And if you wait for a whole second, you get the good old 4 items. And they are presumably the ones that you just happen to attend to before the bar occurs. And they will be then the ones that are registered in short-term memory, a more durable store than the icon, in the visual spatial scratchpad, for example, or in auditory short or verbal short-term memory, or in the articulatory loop. But those are 4. That's 4 items. That's what you can actually report, both for whole report and partial report. If you wait too long, if you wait a second, then there's nothing left in the icon, and you must rely on more durable storage systems. And again, those could be both the visual spatial scratchpad, which we learned about in the first part of the course, or the articulatory loop in articulatory form, or both. They could both be holding those letters, and of course you can hold on to them for a very long time, depending on whether you can rehearse them or not. But that's not the icon. It's gone already by a second. So how does the icon work? Here's one hypothesis. An iconic representation is created the moment a display appears. It's based on a certain amount of neural activation, presumably in an early part of the visual cortex. If the display has high contrast, it's bright, lasts for a long time, or it lasts for a long time, the icon should, in fact, be a little more durable, because activation will be greater. So can we, this is the million-dollar question, increase the durability of the icon by showing the items a little bit longer, or presenting them in high contrast, and then once the display is terminated, it will fade? But can I change the durability of the icon by increasing a little bit the exposure duration? So I don't mean going from, let's say, 50 milliseconds to a second, but let's go from 50 milliseconds to 200 milliseconds. Will the icon be a little bit more durable, and then I will improve partial report accuracy? And this is the question that was asked in the second half of our discussion of the icon, and it turns out the results are a little bit counterintuitive. So here's the hypothesis. It's a low-level visual description that captures exactly what's on the retina in retinotopic form, which means whatever is on the retina in a particular location is represented in the icon in a sort of a mirror image, or a copy, if you like, of that display. I shouldn't use the word mirror image, because nothing is reversed from left to right. Call it a photograph then, a snapshot that preserves distances between elements, contours, and so on. So it's a literal snapshot of what was on the retina, but at the cortical level. And it's the kind of representation then that could support spatially cued partial report. If I ask for reporting an item in a particular location on the retina, but of course the item is no longer present, it's in the icon, I can read that off the icon. So here was the experiment done by Vince DeLolo, and it's a clever one because it doesn't require reporting letters or numbers. You are given an array of dots as in A, briefly displayed, followed by the array of dots in B. Now imagine A is transformed into an iconic representation that's in the visual icon. B then is also loaded into the icon before it fades because there's no delay between A and B. So I see A, it activates all the little dots in their particular location retinotopically. Retinotopic means faithfully representing what's on the retina in a particular location. B then is another retinotopic representation. They should fuse. And notice when they fuse, there will be a dot missing. That's the way the array is presented to the viewer, to the observer. The observer's task is to say, where was the missing dot? And in this case, it would be the bottom right-hand corner. And the way it's done is you actually given an array and you have to point to where the dot is, which dot was missing from the array. And it should be a very easy task because you literally see what I'm showing you on the right in iconic memory, if you will. And I say see in scare quotes because, of course, it's not what you actually see. It's what you derive from what you see, but in an iconic memory representation. So if you do get this fusion, and the precise distances between the dots is preserved in the final configuration, that's good. Now you might expect that presenting the first display for a little bit longer will improve integration, assuming that the longer you allow information to accrue in the icon, given the first display, the better the representation, the more faithful the representation, the longer it is preserved, up to some limit, of course. So the million-dollar question is, what will happen if I start with a brief display of A and followed by B immediately without delay, and I increase the exposure duration of A? Would you get better performance? And so this is, again, to remind you of the task. I show you A for a very brief time. It's a bunch of dots, seemingly in a random configuration. B then, but they are carefully arranged so that if you superimpose them in the icon, if you fuse these two patterns, you will be left with what you see on the far right. And I can vary this from trial to trial, so the gap changes from image to image across trials. And the task is, where is the dot? I'm sorry, not where is the dot, where is the missing dot, rather. And this is what happens. It's a very strange result. So this is the result. It's counterintuitive. So 0 on the x-axis means that, of course, I didn't have any time at all to see the first display. That would be silly. Notice where the red dot is. It's about 10 milliseconds after 0. So that means the first display, look, it's the duration of the first display on the x-axis. It's about 10 milliseconds, and it's immediately followed by the second display, which is also briefly displayed, but the second display of dots is always a constant duration. It's the first duration, the first display, the duration of the first display that's varying. So it's either 10 milliseconds, running your eye along the x-axis, 40, 80, 120, 160, or 200 milliseconds, meaning I'm giving you more and more time to see the dots in the first display. And on the y-axis is the amount of errors you make in saying where the missing dot was when you fuse the two displays. Again, the first display is varying in duration from 10 milliseconds to 200 in systematic steps. The second display, the duration of the second display, is not varying. And I'm just looking to see what happens if I increase the duration of the first display, and I get a very interesting result. The result is that beyond 80 milliseconds, so there's not much change between 10 and 80 milliseconds given the duration of the first display. But if the display is increased to 120 milliseconds, or 160, or 200, the errors you make in finding the location of the dot, of the missing dot, meaning the errors you make in fusing the two displays, increased dramatically after about 80 milliseconds, meaning if the first display is presented for longer than 80 milliseconds, information is being lost. It's very brief indeed. And by 160 milliseconds, if you present the first display for 160 milliseconds, you are losing a lot of information about the location of the dots in the first display. So this shows that visible persistence, at least in this form, this part of the icon, it has the counterintuitive property that it's lost when you increase the duration of the first display. It appears to decay after about 100 milliseconds once the first display is removed from view. It's got nothing to do with the interval between the two patterns, because that's held constant. And again, I'm talking about pattern A versus pattern B, those two dot patterns. And the evidence further shows that it is indeed information that's being lost from the first display when the duration is increased beyond 100 milliseconds, or 80 milliseconds rather. And we can look at the errors that the observers make when they misidentify the location of the missing dot. So when you have lost information from the first display and you falsely indicate where the missing dot was because you've actually lost information about the dot from the first display, what would the errors look like? And you can see, I'm going to show you that in a moment, but let's just, before we look at the results, just go back over the logic. The question is this: where do you think the gap is located when you lose information from the first display rather than the second display? And if the iconic representation of the first display has portions that are missing because of decay, the composite image that is created when the second display is presented will, of course, be incorrect. And this incorrect information, i.e. the lost dot, is expected most often to be associated with the first display if increasing the duration of the first display actually causes, counterintuitively, a loss of specific information about the location of different dots. So the information from the second display should be retained because you don't change its duration. And so the error that is made should be when a missing dot is experienced in the first display because of missing information in the first display. And is that what happens? It is exactly what happens. So look what happens. We again, duration of the first display, not duration of the second, duration of the first display, 10 milliseconds, 40, 80, etc. Percent errors that are occurring as a result of mislocation of dots or misrepresentation of dots in the first display. That's red. And if you go beyond 80 milliseconds, you can see the red line, the dots, the red dots, are coming from mislocation of dots in the first display. The longer you present the first display, the more you start to mislocate dots in that display. And when you fuse that display, which is degrading now, after 80 milliseconds, in fact, a little bit by 120, there's loss of information, by 160 even more, by 200 even more. If you fuse the first and second displays, the errors that you see are coming from missing dots in the first display, from the first display. And you can see that the second display is not contributing very much to the errors. It's the first display that is contributing because, of course, the longer you present the first display, the more information is being lost from the first display. So it suggests that the visible persistence begins to decay about 100 milliseconds after the onset of the display, and it's lost by about 200 milliseconds. But this is kind of different than what we saw in the partial report paradigm, which seems to indicate that information is preserved for not a second, but somewhere near that number. So when we say, well, the icon decays within about a second, this mismatches what we're seeing in this result, which says the icon is decaying by 200 milliseconds. And the answer then must be, well, there has to be two separate systems contributing to iconic persistence. That is a very, very short-lived one that lasts for less than 200 milliseconds, a very short-lived storage system, followed by a slightly longer duration system, also short relative to, let's say, the visual spatial scratchpad, but longer than 200 milliseconds. So two components to the icon, a very short-lived one and a slightly more durable component. And so this is our very short-lived component, and this is our longer duration component. So look on the right, if you look at the display that is the delay from the disappearance of the letters on the screen, 12 letters, to the to reporting one letter with a little bar, and the delay is 300 milliseconds, you're still better than full report. Partial report is still better than whole report. Whole report is 4 and a bit. Partial report, the estimate is around 6. So whatever is preserved in the icon lasts for 300 milliseconds or longer, whereas on the left it's telling you that it's gone. Whatever is presented with these dots appearing very briefly, that's gone after about 100 milliseconds, which means that there are indeed two systems. One's very, very brief and one's a little longer. One lasts a little longer. You can see again, even at 150 milliseconds, what's represented on the left is gone, lots of mistakes, whereas on the right, you can see at 150 milliseconds, partial report gives you an estimate of around 7.5 items in the icon, relative to, again, 4 and a bit for full report. So at 150 milliseconds, there's still lots of information, apparently, in some part of the icon, and in another part, nothing. Pretty much all gone. That's the information on the left is decayed by 150 milliseconds. There's lots of mistakes from that very, very brief display. So there are two different systems, a low-level system of visible persistence that contains a literal representation of a display. It begins to degrade about 100 milliseconds after the stimulus is appearing first, after it first appears, and then an iconic memory system that lasts for a few hundred milliseconds longer after you remove the display, and that can be distinguished from the first system. So notice if I present letters, there's a brief pulse of information, even when they're on the screen, in an iconic buffer that lasts for about 1/10 of a second. Once I remove them, there's an echo, if you like, that lasts for a little longer in another part of the icon. It's a visual echo, of course. So we now can ask, look, is it truly visual, that echo that lasts longer than 100 milliseconds? And is it based on shapes only? Is it fully integrated letters? Is it the location of the letters? Is it even the meaning of the letters? What is represented in that more durable part of the icon? The original proposal was that the icon represented uninterpreted visual features in separate spatial locations, just bundle of features. So to integrate the bundle at each location, the visual information must be selected, and the spatial cue tells you select from this location or from that location, depending upon where the little bar was. So spatial cues and other physical attributes, perhaps movement, for example, or change in contrast should work, but surely not cues on this account that involves conceptual features, such as the category of the item, because if it's bundles of features, at that level, the system is not able to interpret the bundle as being a number or a letter. But it could be possible that maybe that view is wrong, and that, in fact, some of the information in the icon after this very brief duration, this 100 millisecond brief system, but a little bit more durable information, might include conceptual information, the category of the item. So it could be that selection is, in fact, not just based on physical attributes, but on the identity of the object, and that would be late selection. So in a display consisting of a mixture of letters and digits, maybe it's possible to report just the digits, and we need to know if that's true or not. If it's true, then surely the icon, again, that slightly longer persistence in iconic memory, that is made up of perhaps information like this is a digit, this is a letter. We need to find out. And this is how we do it. If indeed you can select on the basis of whether an item is a letter or a number, if you look at the display on the bottom of the screen, there are in fact 4 numbers and 4 letters. Now, there are 8 items in all. I know that with full report, I can only get 4. So if I say, tell me all the letters that you can see, and I'm just relying on full report, I will say I saw K and P if I'm looking at the top row. But imagine if I say, no, report all the letters, I get more than that. I say I saw K, P, C, and N. That surely means I can download or select from the icon information based on the category. So under partial report instructions, if you are able to select on the basis of meaning, I should be better in partial report, where I say letters versus numbers, than full report, where I just say, well, tell me whatever you see. If I ask you whatever you see, you're going to say K7P4 if you look at the first row. If you look at the bottom row, you'll say I saw 6CN2, which means you get 2 letters and 2 numbers. If I can get more than that based on partial report and I rely on the category as the cue, then it means I've actually got category information in the icon. So I'll read you the slide just to make sure we're all on the same page together. To demonstrate that observers can select objects from iconic memory using category information, it must be shown that partial report cued by such information, letters versus numbers, is superior to whole report. If partial report and whole report lead to equal performance, so no advantage for partial report, there's no evidence then that the partial report cues worked. Under partial report instructions, observers would have simply identified as many objects as possible, so in this case K7P4, for example, and then reported just those that fit the category cue, which means I'll get 2 letters or 2 numbers. If I get more than that, there is information in the icon beyond just the shape of the letters or the features involved in the letters and numbers. Okay, so this is whole report, K7P4, 4 out of 12. If in fact I get if I'm asked just to report the digits under those conditions, I'll just say 7 and 4, 2 out of 6 items. So it means that partial report didn't help. I was just downloaded all 4 items and I picked the letters or the numbers depending upon your instruction. But imagine instead I report 7462, then I'm able to download just the numbers, which means the information is tagged with respect to category information in the icon. So here's the relevant experiment using 2 cues. I either use a spatial cue, which means I'm not interested in the category of information represented in the icon. You'll see how that's tested later. There are 2 rows of 4 elements, making a total of 12. Under full report, I can get 4. But I give you a number just after the disappearance of the array. If it's the number 1, report the top row. So you say K7P4. If it's the bottom row, it's the number 2. So you say 6CN2. And if I say 3, just after you've given the sound, the cue 3, I must report as many items as I can identify. That's whole report or full report. Now the timing of the cue is presented in this case at 0 milliseconds, and we'll talk about the minus 250 in a minute, but at 0 milliseconds it means the entire 8-item array is gone, and then I give you the cue, either 1, 2, 3, or 4, telling you which row to report, or just report as much as you can see if it's 3. 250 means there's a delay, and so of course I'm going to lose information from the icon, and so my performance will be worse. Minus 250 means I'm presenting the cue, 1, 2, 3, ahead of time, 250 milliseconds before the actual array occurs. So that means if you hear 1, 250 milliseconds before the array, I will attend to the top row before it occurs. If it's 2, I'll attend to the bottom row. And if I hear 3, it means, okay, you just want me to report as much as I can see. And this is, we can do the same thing now with categorical queuing. So 1 refers to numbers in the display. 2 is letters. 3 means whatever you can derive. It's up to you. Report whatever you see. That's whole report. And again, minus 250 means the category labels 1, 2, or 3 numbers, letters, or whole report 250 milliseconds before the array appears. 0 milliseconds means the array is off the screen by the time the cue occurs, 1, 2, or 3. Or 250 milliseconds, the array has gone and you wait 250 milliseconds before presenting the cue, which again is a number. 1 meaning report the number, 2 meaning just report the letters, 3 report all the items you can see, or as many as you can see, and of course we know you'll be able to get 4. So what happens? Well, if it's whole report, shouldn't be a surprise. We get actually a little more than 4. You get just a bit more than 5. It doesn't really help if the cue is given 250 milliseconds before the array or immediately after the array disappears. And the array is presented quite quickly, let's say for 100 milliseconds before the cue appears, or 250 milliseconds. This is whole report. And of course, notice you would expect that whole report will not vary depending on the delay because it's just a whole report. I will try and report as much as I see, and I can get 5 items here. A little bit more than 5 if you have an advance warning. That's probably due to me knowing what to do, because remember, you've got 1, 2, or 3 appearing at random. They are presented acoustically, so you hear 1, 2, or 3 250 milliseconds before the item array occurs. So you know, I don't have to worry about letters or numbers or top versus bottom. So it helps you just a little bit. How much? Oh, very little. It's 5 out of a total of 8. If there's a 0 delay, and if you're given the cue minus 250 milliseconds before the array appears, you get another half an item, so it's not a big deal. Look what happens, though, if I cue the category. So that means just before the item array, the 8-item array appears, you know, report numbers or report letters. You can get more. Now, how much more than full report? Well, enough that those blue lines, the blue dots, or the blue line made up of those dots, is statistically better than whole report. Not by much. It's about a half. You get about half an item more, give or take. Maybe a whole item. If you look at the 0 cue delay, which means the array is gone, and you hear a 1 or 2, not 3, because the whole report means report everything that you can get, but the category cue means letters or numbers. You're getting an extra item, 5 versus nearly 6. And at 250, you'll notice, of course, there's decay. It hasn't gone completely. You need to wait longer, but you've lost information. If you waited 500 milliseconds, the blue dot and the red dot would begin to coincide. And certainly, if you wait 1 second after the disappearance of the array, they would be the same. But there is category information available. And of course, you would expect that spatial information will give you an even better score. And yes, it does. So if I give you the spatial cue before you see the array, meaning you hear a number that tells you report the top row or the bottom row, before the array occurs, I get 7 and a bit out of 8. If there's no delay, so that means the item have disappeared, the 8 items have disappeared, then the spatial cue occurs. It's a 1 or a 2 informing me I must report the top row or the bottom row. I get 6.5 out of 8. There's a little bit of decay at 250. It's not enough to cause a major loss of the iconic representation, as you know, by 250 milliseconds. After the offset or disappearance of the display, there's still enough information in the icon to help you, but there's some decay. But the moral of the story is both spatial and categorical cues allow partial report to exceed full report. Spatial cues are, of course, more powerful than categorical cues. Success of categorical cues means that information in iconic memory is coded in a more abstract form than just simple bundles of features. And that's a further evidence for a distinction between one part of iconic memory and this very, very brief store that is responsible for visible persistence for the first 100 milliseconds after the onset of an image. So when you are shown lots of dots on the screen for 100 milliseconds, they're activated in their retinotopic form, and then they begin to decay. And then beyond that, there's a longer, more durable system that lasts for between 500 and a second, 500 milliseconds and a second, and that contains categorical information. So I asked some questions. What point would you compare to show that iconic persistence fades over time? You would, of course, compare A versus B, because A is when there's a very short delay, B is a longer delay, and so that's what you would compare to show, oh, look, under partial report, you lose information if you wait too long. What do the results imply in this figure? Does the icon include information about the category of objects? That's B. A, it does not include information, and we know, of course, it does. And what do these results imply? Well, there's a bigger partial report advantage when retrieval is based on spatial information relative to conceptual information. That's true because we've got whole report as the red line, and we can see that the difference between the red and the green is much bigger than the red and the blue line. We cannot base selection from the icon on conceptual information. That's not true. We can. That's the partial report advantage when you get a category Q, so the correct answer, of course, is A. And that is the end of the section on iconic memory.